everybody. Welcome. How's it been? On a scale of 1 to 10, how's the show been? Just throw all the numbers at me at once. Let's see what it sounds like. 11, I like that one. That was good. That's the only one I heard. We'll ignore the rest. My name is Dean Wells. I'm a program manager in the Windows Server Base team. With me, I have Ryan Puffer. He's one of my peers. He's been working on shielded VMs and guarded fabric with me for as long as either he or I can remember. The idea of this session, it really does have just one goal, and that is to scare the shirts off your back with what? What do you think I was going to say? With regard to, if you run sensitive workloads in virtual machines, there are attack vectors that you possibly, more like probably, haven't thought of. The idea of this is for us to show you every single one that we could come up with that would fit into a reasonable 45-minute session, going for the simplest to some that are pretty much incredibly advanced and sophisticated attacks. That's the goal. So let's kick straight into it then. First things first, take a look at this. If you see on the left side, these are applications and infra that we have been protecting for years. Look on the right side, though. Attacking workloads via the virtualization fabric, the industry has had its collective head in the sand for a long, long time. We were the first to do something about this. We did it in Server 2016 with Hyper-V shielded VMs, and we've made that better in Server 2019 with some additional capabilities. So why must we protect the virtualization fabric then? Let's just take a quick look at it. If I'm a VM owner, do I know in any way, shape, or form when I'm running inside my VM world, I'm administering it, do I know if I'm running on a healthy host? I have absolutely no idea whatsoever. Why am I running there then? If I was running a domain controller on bare metal, I would go and look at the data center. I would check the physical security of the cage. I might even ask about operational practices for physical security. Yet with a Hyper-V fabric, a virtual fabric, running on VMware, Xen, it doesn't matter which fabric, they're all subject to the exact same attack vectors. So it's kind of weird that we allow this to happen. So I'm going to show you two adversaries. This is me. I'm the handsome one that doesn't initially start with the idea. Ryan is the mean one, as you can see. Look, scary, right? If you met him in a dark alley, you would run. Well, if you actually started on a topic of conversation with him, that would make you run. But meeting him, not so much. So this is the way it's going to work. You're going to see this screen a lot. We're going to give you attack 1, 2, 3, 4, 5, 6, 7, 8. Each time we do an attack, we're going to actually demonstrate it for you. Ryan and I sat down and did this in our offices and then recorded it into videos. And then we put a script around it and gradually made the attacks more and more complex to show you what sort of things well-informed, well-educated, sophisticated attackers are able to do. And I want to be clear here. These attacks are not unique to Hyper-V. I've said it once, but I'll say it one more time. I can do this against VMware. I can do this against Xen. I chose to do it against Hyper-V because it isn't really fair to just go to the competition, especially when it's applicable to our own product. So we used it against Hyper-V. So Ryan wants a raise, and as I mentioned the other day, the only way he's going to get one is by giving it to himself. So he basically decides that he's going to attack a workload, the accounting system, via some skills that he has, most likely as a storage admin. He's going to come in some way under the covers, and he's going to go ahead and find a way of giving himself that pay rise. Where does he start? Well, he could go for the workload itself, or he could try and find some kind of identity that gives him administrative privileges over the workload, i.e. he's going to start attacking Active Directory. So let's roll into the first demo. That was my PowerPoint roll into the first demo there, and I'll hand it over to Ryan.
All right. So right now, I'm taking the role of someone who's managing a file server. So we have a Hyper-V server and a file server. All the files from the Hyper-V server are stored on an iSCSI target on the file server. So as a file server admin, I can go ahead and copy that entire iSCSI target. You could imagine the same thing for a regular SAN as well. And once you copy it, if the data is not encrypted, you can just double click. You have a full copy that you can edit and modify however you'd like. So we found this awesome tool online called DS Internals, where once you find ntds.dit, the Active Directory database, you can run, I think it's 3 total commands here. And at the end of that, you're going to get all of the hashes for every user in that database. And I promise you, this is real time. It's quite scary. So here we're saying, give us the accounts in the hash format. And there you go. That was everyone in our database.
So I want to be crystal clear here. This is not us doing it because either of us have specific specialist knowledge in AD. And it is true, my past skill, I do have a lot of skill with Active Directory. Ryan doesn't. Ryan did that, not me. Anyone can do this. He found the module on the internet. I didn't know it existed. So that means if you've got a single virtualized domain controller running anywhere on Hyper-V, VMware, Xen, you name it, Anybody that can gain access to a VHDX through a volume shadow, for example, where they don't even have to stop the VM from running, can walk off with it on a USB stick, and within 10 to 15 minutes of downloading that tool, they've got every hash for every single user, and they now start initiating pass-the-hash attacks against your entire forest. Like I said, it's not photos that are being stolen here, it's identities, and it's all because it was a virtualized fabric. Think about it. How do we do that with bare metal? It's way harder to do that with bare metal. We need a way of protecting that data. All right, so the mitigation then, we're going to encrypt it.
Right, so imagine on the Hyper-V server, you realize your file server admin's a just terrible human. So you go and you say, you know what? It's an iSCSI target. To me, it's a logical volume. I can go ahead and enable BitLocker on it. So here, the Hyper-V admin has encrypted the data before it's written to the file server. So when the file server admin tries the same attack again, they're going to be prompted for a BitLocker recovery key because they are not in possession of that key, which is likely in the TPM of that physical Hyper-V server now.
Okay, so if we BitLocker the virtual machine, that does actually block this attack, right? Because the key is known to the virtual machine, not to the storage admin, and the disk is natively encrypted with a derivation of that key. Fantastic. Encryption, however, is something that people often forget to ask a very poignant question about. When someone says it's encrypted, they're like, oh, good, it's safe. There's always a follow-up question, and that follow-up question should always be, no matter the scenario, what is the key release strategy? What is the key protection strategy? Those two things go hand in hand. Well, without a TPM, a trusted platform module, in the virtualized environment, we only have one key release strategy, and that is to type something in. So be very aware that when you encrypt things, you need to make sure that your key release strategy is as strong as the encryption and the workload that you're protecting is sufficiently protected. With virtual machines generation 1 VMs on Hyper-V, we don't have any other means of providing a key to BitLocker other than typing one in at the boot screen. So in this attack then, Ryan decides he's going to collude with me. I'm the fabric admin. So now we've got a storage admin and the virtualization fabric admin, the VMware admin, the Xen, the Hyper-V admin. And he brings me a box of after eights, the thin mints, because that will persuade me. Once done with that, I'm going to log on to the Hyper-V host. But because I'm the Hyper-V admin, the BitLocker encryption on the host is completely transparent to me. That's all we've done so far. We've encrypted the host. We haven't got inside the guest yet because we don't have a technology to encrypt with inside the guest. So all we've done is we've encrypted the host's file system using BitLocker on the Hyper-V host so that the storage admin of the iSCSI architecture can't get hold of it. This particular attack, Ryan decides he colludes with me. I log on at the Hyper-V host where the BitLocker encryption is entirely transparent. It's not even in my way.
Right, so now we're on the Hyper-V server, and the attack's going to seem awfully similar. Since Dean's inside that encryption bubble, we don't have to worry about the BitLocker encryption. It's in place. So we go ahead, find the storage of that domain controller's VHDX, make another copy, and then we can go ahead and perform the same exact attack we did the first time using the offline copy of the database. And one thing we haven't talked about yet that's really important is the VM admin has no idea this is happening. Right? Their VM's still running. You can copy a VHDX while the VM is on.
Okay. So we started by a storage admin. It seems like generally sound advice, right? Just fire us both. We started with a storage admin who just went and stole VHDs. He just harvested all of them until he found something useful. We encrypted the storage using the NTFS and BitLocker capabilities on the Windows host. That mitigated against the storage admin attack. He then colluded with the fabric admin who logs onto the Hyper-V host, and the encryption is now transparently removed. I live inside that encryption bubble. So the suggested mitigation then is obviously fire us both, but how about we now try and put the encryption inside the guest? How do we put the encryption inside the guest as well as on the host? So we're double encrypting the data. That way, even the fabric admin, theoretically, can't get at the data inside the guest.
Okay, so we're repeating the same attack. This time, the VM is encrypting itself. So we're on the Hyper-V server, and we go ahead and we find that VHDX again. But this time, since the VM has encrypted the data before it got saved into that VHDX, it's going to look a lot like our first scenario, where the person who's trying to open the VHDX needs to have that BitLocker recovery key to get access to the data. So right there, we were able to thwart the Hyper-V admin and the file server admin from accessing this data.
Okay, so that seems to work. So let's go ahead and reset our environment then. Put all these mitigations in place down the left. We can now see what mitigations are in place. And now, with attack 3, I'm going to abuse my fabric admin rights, and I'm going to add a malicious bootloader. Anyone know what I mean by that? I'm going to put some piece of software on something in the boot path that intercepts Windows booting, does something malicious, and then probably hands control back over to Windows in a way that hopefully nobody noticed. The classic rootkit attack. Okay, let's see what that looks like.
Okay, so with the Hyper-V admin, presumably at some point in time, this VM has to go down for maintenance. So before it comes back online, we're going to go ahead into the settings, and we're just going to go and attach a DVD drive file for our malicious bootloader. And because the VM is encrypting itself, the VM admin already expects to have to enter a recovery key or the regular unlock key to actually decrypt this volume. There's no TPM to automatically do this. So I made my bootloader look identical to the default one, which isn't very hard with that interface. It's quite simple. And the trick is here, this is my bootloader. Admin types it in like normal. I save a copy for myself, and then I pass the password to the real bootloader. So the VM still starts up correctly, and as far as the VM admin is concerned, everything's normal. But I have a copy of the password.
So, crystal clear on this one. The only way of encrypting a Generation 1 and most other VMs that are out there today in the wild, whether it be in the cloud or in foreign third-party hypervisors, is by using a BitLocker boot time password. If you train administrators to get used to entering BitLocker boot time passwords, next time you call them to tell them to enter the BitLocker boot time password, what are they going to do? They're going to happily enter it. Why did they have to enter it? Because the Hyper-V host went down for maintenance. So we decided to shut the VM down as well so it could apply some patches it was waiting for as well. Therefore, when it was booted back up, we had to call the AD admin to tell them to enter the password, which he just politely entered into Ryan's malicious bootloader. That's it. We own the machine again. How do we stop this? Let's go ahead and show you how we stop it by using some better technologies.
Right, so the goal here, how do we stop the admin from ever entering that password? And we think back to physical machines. Physical machines, like your laptop, we use a TPM. Store the key in there. That'll automatically release the key to BitLocker so long as the security state of your system hasn't changed. So let's give the VM a virtual TPM. And when we give it a TPM, in this case, we've still added the malicious bootloader. It's still going to try to boot from it, but we've also added secure boot. So we have secure boot and the virtual TPM. Secure boot says only Microsoft-signed bootloaders can run on this machine. So when Hyper-V goes through this list of things to boot, it's like, oh, I should try the DVD first. Well, the first thing we're going to see is this bootloader is probably not signed by Microsoft because typically attackers don't work at Microsoft. So when we see here, we're going to go ahead and boot up the VM. And the awesome part is it's just going to work because it's going to skip right over the malicious bootloader because it wasn't signed by Microsoft, so secure boot thwarted it, and the virtual TPM made sure the admin wasn't expecting to have to enter a password should one have appeared anyways.
So does everyone understand there? So we've now thrown away all this legacy stuff. We've got some modern things in play by literally borrowing the silicone technologies that we've been reliant upon for quite some years now, UEFI, secure boot, TPMs. We've made Generation 2 VMs support those. The way UEFI works is very different to the PCAT or PCAT BIOS of old. Before it hands control over to an operating system loader, it takes a look at the signature, the co-signing cert, or the hash of the OS loader, and it tries to ensure that that thing exists in one way, shape, or form within a variable in UEFI called DB, which is the blessed database of operating system OS loaders that we will hand control to. And it subsequently checks that it does not exist in some way, shape, or form within the DBX, the database of excluded bootloaders. That means that when it tried to boot Ryan's malicious DVD bootloader, it took one look at it, could not find the signature in either of those variables, and implicitly ignored it, and went straight back to the C drive and booted Windows. The attack was thwarted. Okay, next one then. Ryan and Dean realized that we can pre-infect VMs. Okay, so we're really on this now. I also want my pay rise. We don't seem to be able to get into a running VM. How about pre-infecting a VM? Well, every VM, I would say 99% of VMs that are born from template disks. In the Windows world, that's a disk where you build the perfect OS instance in your clean room, and you call that your golden image. You then run a tool called sysprep. You're all nodding at me. You know what I'm talking about here? You run sysprep, and you save it off to a library somewhere or other. What if we attack that? What if we add a keylogger into the template disk? That means every existing VM, okay, you guys are fine, but what about every new VM? They're born compromised. Let's see how that attack looks.
Right, so we're back on the file server now. Template disks are stored here. Someone's already made a template disk. It's ready. It's the one that's going to be deployed by default on Hyper-V. So we open up File Explorer here, and I already wrote a keylogger. And we just need to find a way to get that to automatically run inside the VM. Now, there's tons of different ways you can make this happen. I'm just going to go and look through the group policy script directory, see what was already put in there as things that should run on first boot. So we scroll through here, we go in there, and we see that there's something about printer drivers. Must be there's some sticky driver that needs to be installed every time. Well, we'll just go ahead and rename that file. Don't need that. And we're going to go put our keylogger in there instead. And what's going to happen is when this machine boots up, every single VM started with this image is going to have that keylogger in it. And the VM admin's none the wiser. They just said, hey, give me a VM. And it came up just as they'd expect. So from the Hyper-V's perspective, they go ahead and grab that VHD from the file server, and they're going to go over here, copy it over, create a new VM wrapper around it. And once we go ahead and connect all that up, we will be able to quickly boot up the VM, and whatever software I put inside that template disk will be available to run at a scheduled time. So nothing here would even give the Hyper-V admin an indication of this because they're just using a VHDX. They don't know what's in it. They were just told to use it as the template disk.
And what would you imagine that this script that installs the keylogger does at the end? Replaces the legitimate script and removes itself. Now you don't even know it was there to begin with. This can happen on your existing template disks today. So here's a suggested mitigation. We're getting into some technical terms now. We need to use signed template disks. The process of signing is the process whereby you hash some large chunk of data and you produce a statistically unique result of some length depending on the algorithm. What you then do is you encrypt that hash with a private key of a known certificate pair. The private key is used in this case to encrypt, not decrypt, because you want people with the public key to be able to perform the same operation in reverse to validate that the hash is good. Hence, you use the private key to encrypt a hash to create a signature. This is what we refer to as signing. In the case of a signed template disk, we're going to take a hash of that disk simply by looking at every single cluster. We hash it. We then get the next cluster. We hash it. We concatenate the two hashes. We hash them again. We look at the third cluster. We hash it. We concatenate the last hash, which was the first two clusters, hash it again. And we repeat that ad nauseum right the way through to the end of the disk, at which point we do some clever magic with cryptography, and we produce a signature that we store in a volume signature catalog file. A trusted admin is the one that performs all this. And then during instantiation, during provisioning of brand new VMs, the Hyper-V host, is responsible for recomputing the signature and comparing it to the whitelisted policy. This is the process of secure provisioning using signed template disks. Let's implement that. See what happens to Ryan's attack.
Okay, so we have the same thing as before. We have our keylogger, and we want to put it on the template disk. So we're going to go ahead and find that template disk again, repeat the same attack. So we go through our file share, find the template, make a double click, open it up. Find the spot where we're going to put in this keylogger. And as part of our templatization process, we want to make sure you don't make a mistake. So this disk was marked as read-only. Obviously, if you change this disk, you're going to make a lot of people unhappy. So we're like, let's make it easy on the users. But very easy to undo that, just an NTFS attribute. So we can go in disk part here and say, let's make it read-write and repeat the same attack. So now we can go access that VHDX again, scroll down. We can go find our script, copy, paste, modify, and we're good to go. So we've saved this disk in the file server perspective. We think everything is perfect. But on the Hyper-V side, we know that this disk has a signature on it. And so we're going to use a different provisioning process to say, hey, before you actually go and start up this VM, also verify that signature. And this process does the same thing as the original one. It recomputes the entire hash of the disk. And once it finishes that process, it's going to compare it to the one in the metadata. And it's going to say, is this what I expected? And what we're going to see here is no. Even though the metadata said this should look like this, when we computed the hash, something had changed. So we are not going to deploy this VM.
So now we're at a point where you can't copy a VHDX off as a storage admin because the storage itself is encrypted on the host. You can't copy it off as the Hyper-V admin because the VM is encrypting itself. You can't actually steal the password boot key because there isn't one. It's using a TPM to release that. And you now can't attack template disks because they're signed by legitimately trustworthy admins, and then those signatures are stored in a trustworthy location, and they're leveraged every single time a trustworthy host provisions a brand new VM from a signed template disk. All of those attack vectors have now been mitigated. So attack 5, Ryan has been fired. Yes. Now it's just me. I get his salary is the way I look at it. It doesn't matter, he's not here anymore, so I'll take it. So I'm going to use a memory dump to attack a VM and steal the BitLocker key. Holy camoli. So what we're going to do is we're going to try and attach some nasty little debugging tools to the processes that run the VM. The VM doesn't know it's a VM. It's like being in the matrix, right? You don't know you're in there. So what we're going to do in the matrix level itself outside it is we're going to dump all the memory of that and then start walking through that content using publicly available tools that he downloaded from the internet. That's why he got fired. He downloaded them in Microsoft and we fired him. Seems like a good idea. And extract the BitLocker full volume encryption key, which we can then throw into it by merely taking a copy of the disk and mounting it on, I think there's a tool called DiskLocker on Linux that will allow you to throw a BitLocker full volume encryption key at a disk that's encrypted, and it will just go, there you go, it's decrypted now. All right, so let's see how that looks.
All right, so our VM is running. Everything's normal. And all we need to do is go ahead and grab a dump of that. There's a lot of ways you can grab a dump of a VM. I chose perhaps the slowest way, which is livekd. And go ahead and say, hey, go dump all this memory to a file. A couple minutes later, you're going to go get a whole copy. Volatility is a memory inspection framework. So there's a plugin for it for BitLocker. And what it does is it steps through all the memory in that dump, and it looks for the pattern of a BitLocker symmetric key. That's the one that encrypts every time you save. And sure enough, a little bit later, there's all the copies of the FVec. The fact that there's multiple is just a side effect of how metadata is stored in memory for BitLocker. But you'll notice they're all the same. And, well, there's a couple actually, but there's two important ones. And you'll get them out, pass it into a tool called DiskLocker, available for Mac and Linux, and that will actually let you decrypt the disk.
Again, freeware, downloadable, nothing internal to Microsoft here, and we still managed to get at the machine. So now the problem, where was the problem really at this point? It was on the host. The host allowed us to run software that a Hyper-V host, a VMware host, a Citrix, a Zen-host, whatever it may be, shouldn't really be allowing us to run. Why would we be running livekd debuggers on a Hyper-V host that's running sensitive workloads? You could argue for support incidents. Well, they are the exception, not the rule, and there is often friction with security, usability, and supportability. I would argue that if you're running domain controllers on a Hype host, debugging tools should not be permitted until special circumstances in your ops processes have been met. This is a requirement. We have to start implementing these things. So the suggested mitigation here then is to do what? How about we use code integrity policies? Who's heard of Device Guard on Windows? Quick show of hands. Not many, okay. This came out in Windows 10, then Server 2016, and it's only been hardened and strengthened and matured in Windows Server 2019. It is a way of enforcing code integrity inside the hypervisor, which means code integrity can even be enforced against kernel mode components. You could write a code integrity policy now on Windows 10, Server 2016, or Server 2019 that limited the drivers it could load, and it could get to the point where Windows would be forced to blue screen because you're not letting it load the drivers it needs rather. Now, that's obviously the negative use case. The positive use case is it allows us to eliminate the use of things like livekd. So let's go ahead and do that.
Right, so we're going to repeat the same attack. We wrote and enforced a code integrity policy here. The policy says anything from Microsoft is fine, but we explicitly excluded the livekd debugger, also any other debuggers that we produced, because those are still signed by us, but we don't want to allow them. And of course, the volatility framework, which had we gotten that far in our attack, would have also failed because it's not signed by us. It's not authorized by this policy. And what I'm doing now is just showing you with Get Computer Info, there's the device guard status. You'll see that we have hypervisor enforced code integrity running. That's what blocked us from running livekd in the first place.
Okay, so how do we stop that? As a malicious admin, remember who's left. Ryan's been canned. He's just taking over my role of explaining the video. It's me doing this now. I'm a Hyper-V admin. If I'm in the Hyper-V admin group on a Hyper-V host, what other group am I very likely to be in as the Hyper-V admin? Domain admin, maybe, or at least local admin. CI policies, where are they stored? Anyone know where we store CI policies? They're on the file system. What do you think I'm going to do to the CI policy? Not for me. I'm going to go find that CI policy and eliminate it.
All right, so as a local admin on the Hyper-V server, we're going through now and we're going to go find that CI policy. So we know LiveKD is blocked, so we say, oh, well, that's fine. Code integrity, we can fix that. So we go ahead and open up System32 code integrity. Conveniently, the policies are always named the same. So we go ahead and find that. There's our policy. We say, oh, you know what? Not for me. Rename it something else or delete it. When Windows reboots, it will see there's no policy there, and it's like, oh, that's fine. No policy today. We'll just go ahead and allow whatever. Give it a nice little reboot. Once your server gets back online, go ahead, try your attack again. Everything's going to work. And that was super easy because you were the admin of that machine.
Dang it. We thought we had it with a hypervisor enforced code integrity policy that can even block kernel mode components. It looked like he was done, or I was done, I guess. Well, as the local admin, I simply identified the policy, either removed it or replaced it with one of my own choosing. Well, we saw that attack when we designed Device Guard. So we came up with this notion of signed and locked policies. Policies that can have a signature created from them and then store the certificates for those signatures in secure UEFI variables that can then be compared as Windows boots. The hypervisor comes up. It's got enough of the stack loaded. It sees a hypervisor-enforced code integrity policy has been put into place. It looks at its signature. It compares the signing certs that are inside UEFI now. Is that indeed the cert that signed this policy? No, it's not, because one, the signature doesn't exist because the policy doesn't exist, or two, maybe I tried to replace it with a policy that allowed those tools, but I didn't have access to the certificate to create the right signature. What does Windows do? Well, let's show you what Windows does.
All right, so this time the admin of whoever decides to go make this code integrity policy said, you know what, we're going to sign and lock this policy when we deploy it. So it's already in the UEFI variable, so we're going to go here and try to replace it. In this case, we know there's a CI policy already, so it's probably suspicious to go from CI policy to no CI policy. So we just wrote our own CI policy that allows the tools we want and are going to put that in place of the existing one. So trying to get a little sneakier here, but you'll notice as we keep going through these attacks, I'm making more noise. All these
I am actually.
You are, yes, I'm fired. But my ghost is making more noise. File auditing could catch this kind of stuff. We're rebooting the server, we're causing downtime. So these attacks are getting much more difficult as we go. But when we booted up this time, we had a policy that was configured to say, do not allow a CI policy that's not signed by our company to boot on this machine.
So let's just be crystal clear here. That is not fictitious. Windows can do that today. Let's just be very clear about what circumstances you would do that under. You would have to ask, if you're the consultant or if you're the customer, you have to make this decision. Would I prefer this workload, this VM, to fail rather than have it run in a compromised state? If the answer is yes, then locked UEFI secure hypervisor enforced code integrity policies are for you. If not, don't do that, because if anybody makes a mistake or somebody malicious attacks it, the machine will blue screen. This is a deliberate choice on Windows' part. So when I tell you that certain competitors claim to have a product that competes with shielded VM and guarded fabric because they call it encrypted, it is not the same thing by a million miles. It is shy by 95% of our feature set, my off the top of the head estimate. I think you know who I'm talking about. They call it encrypted VM. Shielded VM is way more than that. Encrypted VM is about virtualization plane attack vectors and putting some protections in for storage attacks or offline attacks. Ours is about protecting from malware on the host and from malicious admins across the fray of admins that exist in your workspace. Storage, network, Hyper-V, domain, all of them. That's the goal here. The competition can't do this. These are not the same set of technologies at all, even if the branding may appear to be similar. All right, next one then. So I'm running out of options, and I'm forced to take yet one further risk. So I'm going to take a full memory dump of the entire host. The process here would be get the VMs running that I want, switch on crash dump on Windows Server, tell it to do a full dump, and then go and grovel through that entire dump file, which on a Hyper-V host could be pretty massive. 256 gig dump file, and now I'm going to use that software that Ryan showed you earlier to grovel through that. I don't care if it takes 72 hours, which it probably would. Having had he and I watch this thing on a 256 gig hype host, it probably would take about 72 hours to run. But if the VMs were running and they were present in memory, will it work? Yes, it will. It will find those BitLocker full volume encryption keys, and I still succeed. So let's show that happening.
Okay. So here we are. We're on the Hyper-V server again. We know we need to make some kind of attack here. So the first thing we're going to do is go and make sure that we have full memory dumps enabled. That's easy to do in the UI. Go ahead, go to settings, and verify here. We have complete memory dump configured. Awesome. Now all we got to do is cause a memory dump. You can do a lot of terrible things to cause this. Write a really bad program, do something weird in the hardware, but however you get there, trigger a dump. Come back a couple days later, probably when that thing is finished saving. And then you'll have a giant file. In my case, I chose a small one for the purposes of this demo. And then you can go use the same volatility framework, scan that thing. And the benefit this time is you get not only the VM's encryption key, you're going to get all VM's encryption keys and the hosts. So
Yay! Now I've got it all. So I just got the keys to the kingdom. There is nothing that's secure anymore from this because I got the Hyper-V host key itself, so that's that BitLocker bypassed, and then I got all of the VMs running there, one of which was a domain controller. I'm good to go. It's getting pretty difficult to imagine how we would thwart this. But we actually have two ways of thwarting this. One of the things that we can do is we can actually encrypt the crash dump files. Windows supports that as of Server 2016, as of Win 10. We can encrypt crash dump files, and we can measure that encryption on the external attestation service, and we can even have it measure keys. So we can have an external device that knows what trustworthy is, take a look at a Hyper-V host, refuse to give it keying material unless it measures up to what its assessment of healthy is, and it's got crash dump encryption switched on, and it's using a set of trustworthy keys. We can measure that in Windows today. You have been able to do that in Windows for just over 2.5 years or so. Again, that is a capability that, as far as I know, is unique to Windows. In this particular case, though, we're going to focus on something a little different. We're just going to go ahead and see if we can bypass this process and see if I can just grab those keys. So Ryan's going to show you exactly how we attack this one rather than using encrypted memory dumps.
Right. So here we are. We're going to do the same thing. We want to take that crash dump here. But this time, the important thing about crash dumps is your VM already has to be running to get anything useful out of it. The encryption key is only in memory once that VM has started. And in this case, we can't even start the VM because we have enforced attestation here, and the key is being held hostage by an external server until this host is proven to be healthy. So what we're doing now is running a quick command to say, hey, why couldn't I start that? Why am I not healthy? And you'll see here I'm not a guarded host because my host is insecure. I have dumps enabled, and they are not configured to be encrypted by a key trusted by your security admin.
Again, all real today. There's this in Server 2016. It also exists in 10, and it also exists in an enhanced form in Server 2019. If you take a review of everything we've done so far, then we've got virtual disks encrypted on the file system of the host. The VMs are encrypting. We've got modern hypervisors and TPMs in play. Signed disk templates. We've got restrictive signed UEFI locked code integrity policies. We've got external host attestations that understand what trustworthy is and refuses to release keys so that the VMs can't even be powered on. And we've got, tightly coupled key release and the health attestation authority. Now, what exactly does that boil down to in terms of the features that we had to build? So let me show you exactly what this is, because this is where you really start to have the ability to ask questions about any solution you might be looking at and say, well, does it support per VM encryption keys? Does it support guest virtualization-based security, which is a VBS technology that Microsoft invented? Does it have forward secrecy? Does it support synthetic TPMs? Can it do secure and measured boot? Does it do health attestation? All of these things are part and parcel of an overall solution to ensure that the virtualization plane is not a unique attack vector regardless of the workload. And obviously, as we've already mentioned, this is something that we have in both Server 2016 and 2019. We refer to them as shielded VMs and the overall fabric as a guarded fabric. The attestation component is a standard role on Windows Server called the Host Guardian Service. So let's show you quickly what you need then. In terms of the requirements, I need a place to run shielded VMs that is known to be healthy. That requires, obviously, an off-box attestation service. So a way to verify that the host is in a healthy state. I need a way of releasing keys only to healthy hosts. I need tamper-proof source media, and I need a secure way to deliver other secrets into the VMs at provisioning time. Secrets such as volume signature catalogs that identify secure, signed, trustworthy template disks. We do one of those with guarded hosts. That's just a term we use to describe a Hyper-V host that has been attested as trustworthy. Then we have the Host Guardian service. This is typically implemented as a 3-node cluster, and it's there to measure the health of the Hyper-V host before releasing keys to them. Next, we have the signed template disks. You saw that technology in play earlier where we tried to modify the template disk, and the Hype host refused to provision the new VM because it didn't match a trustworthy one. We have the shielding data file, which is just the term we use for a big lump of secrets that are encrypted, they are protected, and they're put inside the VM on its C drive during provisioning where they're decrypted so that the system has an unattend file, for example. You don't even want the unattend file being attacked. There might be certificates you wanted to deploy through the shielding data file. This is what a complete guarded fabric looks like. Lots and lots of Hyper-V hosts, and then they all trust a given host guardian service that can determine whether or not they should have keys released to them to run or live migrate shielded VMs. Even live migration is encrypted. So as a VM that's running, which is shielded on one host, attempts to send it to another, it will force the other host to attest, make sure it can prove it's healthy in the same way. If it won't, then it will not send to the VM. If it can prove it, then we will encrypt every single packet while we live migrate the VM from one host to another. The vTPM in the guest is not bound to the TPM in the host because that would destroy a good amount of the good uses. The use cases for virtualization is the ability to balance load would be destroyed if I can't move it from one host to another. So, very, very quickly then, here's the summary of what you get new in 2019. It's quite the laundry list. We now support Linux shielded VMs. Fallback configuration. Think of this like preferred DNS server, alternate DNS server. We now have preferred host guardian service, alternate host guardian service. Okay, seems like a logical addition. We support something called offline startup of shielded VMs. This means that if you've got a branch office where sensitive VM workloads need to run, you'd ideally like to have them shielded there. Agreed? That would be a good place to do it. There's no physical security. But what if the WAN goes down? Now you've got a potential denial of service attack, an inadvertent one or a deliberate one, in a branch office that you may not want to have VM workloads unable to boot up because they couldn't be attested. So we built something called offline startup. It requires that the Hyper-V host be attested as healthy once by a known legitimate host guardian service, and it then caches the key by sealing it into the TPM indirectly. What this means is when that host comes back up again, if a host guardian cannot be reached, it will attempt to unseal the keys needed to power on the shielded VM. As long as the boot state, the security state of that Hyper-V host has not changed since the time it was deemed healthy and the keys were sealed into the TPM, then the TPM will unseal them. If anything about its boot measurements have changed, it will refuse to unseal the key, and now we need the host guardian back in play. So this is actually a secure offline caching mechanism. What we do is we recommend that you combine fallback and offline to create a mode where you can actually have the host guardian service run out in the branch office as well, get this, as a shielded VM. How does that work? Because you have the Hyper-V host configured with a fallback HGS. Its primary host guardian is the shielded VM running on it. So as long as it's running, it can work all locally and power up and live migrate all the other shielded VMs. As soon as that one goes down, i.e. the shielded VM's down, it will either go across the wire to the alternate, or if that's not available, and presumably the alternate would be in the data center across the WAN, if that is also down, what will it use then? The cache. The cache is the final point of failure. And we designed this deliberately to state that you do not weaken the security model. We have merely stretched it. We have stretched a promise of security using this mechanism. Because if the machine was healthy at point time 1, and now 3 days later, it's in exactly the same health state at point time 3, who cares? You can have the key back, as long as the host guardian policy said that that was permissible. That is part and parcel of Server 2019. Single host binding. Well, who's heard of a privileged access workstation? Okay, so we have a reference architecture that we've put together for running privileged access workstations on Windows 10 machines that are also running Hyper-V. The OS is nothing more than a Hyper-V appliance. Your daily desktop machine is a shielded VM, and so are each of your privileged access workstation machines. This is why we built single host binding. We double encrypt all of that information about the TPM such that it can only be unraveled on this one machine because it's the only machine that's got the TPM keys sealed. That way you can't move the poor off. If they stole the storage media in the physical machine, doesn't matter. It doesn't have the TPM. If they change the measurements of that machine, it could potentially actually break it. If they try and attack the TPM, they're still not going to get there. It's double encrypted. You understand what this one is for? It's for making sure a shielded VM cannot be migrated and run anywhere other than the machine on which it was born, and it is now locked down to by virtue of the TPM inside it. A new simpler attestation mode for those of you that want to try this out and see how shielded VMs work, but you don't want to go through the rigor of deploying TPM or hardware-based attestation. That's a fairly complex setup to get all of these rigorous health measurements in place. The new mode that we've built, and Ryan and I went back and forth on this for about 6 months, is incredibly simple. We call it host key attestation. You go to the Hyper-V host, you run a commandlet and generate a key. You spit that out into a file, and you give that file to the host guardian service. Job done. It did not attest to the health of the host. It did not attest anything. It merely said, you've got the key. Good. You can have the keys for this VM. It is not the same thing, but it does allow you to test whether the shielded VMs work in terms of your environment, because it doesn't impact how the shielded VMs run, how they're live migrated, what the performance hits are. The only thing it does differently is the decision by which it says, is the host healthy? Now it's the possession of a private key instead of a rigorous health dance. But it does allow you to test shielded VMs and see if the rest of the process works for you. Last but not least, we improved VM Connect and PowerShell connectivity because they were, PowerShell Direct rather, they were disabled with shielded VMs. We've restored VM Console Enhanced connection and PowerShell Direct. We're still not allowing basic connections because they're a little bit worrisome, emulating VGA devices and basic keyboards. It seems like too easy a way of attacking the machine. And last but not least, we've improved some of the deployment tools. Shielded VMs also provide one lovely little advantage. If you've got a workload that currently you can't virtualize due to a compliance requirement, like the payment card industry, merely moving that workload into a shielded VM means you attain the compliance bar just because it's shielded. You didn't do anything to the workload, you didn't do anything to the OS, you merely virtualized it, shielded the VM, and now you're compliant. And that's true for many other standards as well. Okay, that's pretty much everything that we had for this brief look into shielded VMs. There are a number of related sessions. There's one that's running tomorrow. It's in that room behind you. So first of all, thank you for making the trek all the way down here. You're going to have to do it again tomorrow if you'd like to see everything else that's going on in Server 2019 security. There is also a very interesting one. How many of you have SQL databases? How many of you would be interested in knowing how SQL can encrypt data without imposing a significant performance hit on a SQL host that is deemed to be not trustworthy? So the SQL host, like the Hyper-V fabric, can be deemed untrustworthy, and yet it can still hold encrypted data and have keys given to it by the database callers to decrypt that data without significantly impacting performance. That's what BRK3057 is. I make a brief guest appearance in that session to talk to you about how attestation works, while Jakob will walk you through how the rest of the technology works. It is a pretty phenomenal invention, and we refer to it as VBS enclaves. SQL is the very first consumer of that, at least for a server workload. And then there's also System Guard Runtime and Zero Trust Networks, which is a blog I recommend you read. Everything else in here, this deck, is fully available to you, so you can literally download this. All of the videos will be intact, and so you can watch it again at your own pace. So thank you again for your attention, much appreciated, and I'll hopefully see you tomorrow.